Okay, this is going to be the practice problems for Module 14, and I thought I would go ahead and write out the equations that you will need for this module, and I'm not going to take the time to explain these because we've gone over that in the lecture. This is an R. Okay, so those are the formulas you would need to know, and the one constant that you would need to know, which you will be given, is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. Okay, that's equal to K. Okay, so those are the formulas that you would need to know, and we will jump in, get going then on the first problem. Problem number 1 tells us that we have a positive 2.3 megacoulomb charge, and it is 35 centimeters away from a fixed charge, and we are told that the electric potential, which is V, is equal to negative 4.6 times 10 to the 7th volts, and then we are asked what is the fixed charge. Okay, so this will just be an application of our formula that electric potential is equal to K Q divided by R. We want to know what is the fixed charge, which is Q, so we're going to rearrange this equation, and we would get V times R divided by K is equal to Q. Okay, so then we can just plug in the values that we have. So V is negative 4.6 times 10 to the 7 volts, and I'm going to go ahead and put a volt is a Newton meter over a Coulomb, and we'll multiply that times the radius, which is 35 centimeters, but we need to get that in meters, so it would be 0.35 meters, and then we will divide that by K, which is 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. Okay, so all the meters are going to cancel, the Newton will cancel, one of these C's will cancel, we'll be left with just a C, and that's the units for charge, coulombs. So then we get that Q is equal to negative 1.8 times 10 to the negative 3 coulombs. Okay, so that is question number 1. Okay, number 2 gives us the following information. We are told that we have a 3.4 times 10 to the cube volt potential, so that would be V. And it says that it experiences a potential energy of negative 12 joules. So potential energy equals negative 12 joules. What is the particle's charge? Okay, so what is the charge? So in other words, we are trying to find Q, lowercase q. Okay, so then we use the potential energy is equal to the charge times the electric potential. So potential energy divided by the electric potential will give us Q. So negative 12 joules, and a joule is a Newton meter, divided by 3.4 times 10 to the third volt, which is a Newton meter over coulombs. That's going to equal Q. So the Newton meters are going to cancel. You'll be left with coulombs. And what you should get with two significant figures is negative 3.5 times 10 to the negative 3 coulombs is equal to Q. Okay, number 3 tells us that we have a negative 5.1 millicoulomb charge. And it is placed 2.20 meters from a fixed charge. And the fixed charge is 5.8, a positive 5.8 millicoulombs. So this is the fixed charge. This is the one that is free to move. And the question asks, if the freely moving charge moves 2 meters toward the stationary charge, what is the change in potential energy? And then did the potential energy increase or decrease? Okay, so we know, so it says what is the change in potential energy? So that's what we are trying to find. And we know that the change in potential energy is the charge, the moving charge divided by or times delta V. Okay, so the first thing we have to do is find delta V. So we will find the final voltage and the initial voltage. So the final, it's KQ divided by R. So this is going to be 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. Multiply that times the Q, which is the fixed charge, and I'm going to change this to coulombs, so it's going to be 5.8 times 10 to the negative 3 coulombs. So I did there is divide by 1,000. And then we're going to divide that by the radius, which for the final, it says that it moved 2 meters toward the stationary charge. So if it started out 2.20 meters, then it's going to be 0.20 meters away. So then what we get for VF, if we do that math, we will get that VF is equal to 2.6 times 10 to the 8th volts. Okay, and then we'll do the same thing for the initial. So the initial is just going to be the same equation that we did for the final, except that the radius is going to be different. So the radius, instead of being 0.2, it would be 2.20 meters. So what we will get for VF or VI is 2.4 times 10 to the 7 volts. Okay, so now we can go ahead and calculate delta V, because delta V is equal to VF minus VI. So we'll take 2.6 times 10 to the 8th volts minus 2.4 times 10 to the 7 volts. And so the delta V is equal to 2.4 times 10 to the 8th volts. Okay, so now we have everything that we need to calculate the change in potential energy. So the change in potential energy is equal to Q delta V. So Q, which is the charge that is free to move, is negative 5.1 times 10 to the negative 3 coulombs, and we will multiply that times 2.4 times 10 to the 8th volts, which is a Newton meter over a coulomb. Okay, so the coulombs are going to cancel. You'll be left with Newton meters, which is a joule, which is good for potential energy. So the change in potential energy then is going to be negative. So it's going to be negative 1.2 times 10 to the 6 Newton meters or joules. And then the question asks us, did the potential energy increase or decrease? Well, because it is negative, that tells us that it decreased. Okay, so that is number 3. Okay, number 4. We are given a negative 6.5 millicoulomb charge that has a mass of 0.0015 kilograms. and it's going to travel from the negative side of a 1-volt battery to the positive side. It's going to travel negative side to positive, and we are told that it is a 1.5 volt battery. Okay, so then the question then becomes, what will be its speed when it reaches the positive side of the battery? So it says if it starts at rest, what will be its speed when it reaches the positive side of the battery? Okay, so if it starts at rest, that means it's going to have potential energy. And when it starts moving, that potential energy will be changed into kinetic energy. So potential energy is equal to QV. So that's going to be negative 6.5. I need to change that to Coulomb. So negative 6.5 times 10 to the negative 3 coulombs. And then we were given the voltage as 1.5 volts. A volt is a Newton meter per coulomb. So coulombs are going to cancel, and the potential energy will be equal to negative 9.8 times 10 to the negative 3 Newton meters, or, I'm ahead of myself, Newton meters, which is a joule. Okay, so if the potential energy is negative 9.8 times 10 to the negative 3, then we know that that when it moved, that potential energy would get converted to kinetic energy. So the initial kinetic energy would be 0, but the final kinetic energy would be 9.8 times 10 to the negative 3. Okay, so kinetic energy is equal to 9.8 times 10 to the negative 3 Newton meters or joules. Okay, so then the last thing we need to do then is what we were asked to do was find out the speed of this negative 6.5 millicoulomb charge. So kinetic energy is equal to 1/2 mv squared. So we're solving for v. So kinetic energy divided by 1/2 m. And if we take the square root of that, that will give us v. Okay, so the kinetic energy is 9.8 times 10 to the negative 3 Newton meters divided by 1/2 times the mass. And the mass is 0.0015 kilograms. And we'll take the square root of that whole thing. Okay, so I'm going to go ahead and change this Newton to a, so it was a Newton meter. So a Newton is a kilogram meter over second squared. Okay, so you'll see that the kilograms are going to cancel. You're going to be left with meters times meters, which is meters squared over second squared. When you take the square root of that, you will get meters per second. So doing that math, we get that V is equal to, with two significant figures, 3.6 meters. What is wrong with this? I apologize. This whiteboard is acting a little goofy today. Okay, so the velocity of that negative 6.5 millicoulomb charge is 3.6 meters per second. Okay, question number 5. We have a positive 1.5 coulomb charge, and it has a mass of 42.3 kilograms, so a big charge. And it's placed 1.4 meters away from a fixed charge, which is 4.4 coulombs, a positive 4.4 coulombs. So this is the fixed. This is the one that can move. It's free to move. And it says if it starts from rest, how fast will it be traveling when it is 2 meters away from the stationary? Okay, so the final is that it's going to be 2.0 meters. Okay, so if we think about these two charges, they are both positive, so they're going to be repelling each other. So this charge that is free to move would be moving away, and in this case, we want to know how fast it will be moving. If it starts 1.4 meters away, how fast will it be moving when it is 2 meters away? Okay, so in order to get the speed at which it is moving, we need to know its kinetic energy. And in order to know its kinetic energy, we need to know the potential energy. It started at rest, so we first need to figure out the potential energy. And so the change in potential energy is equal to Q delta V. Okay, so we first need to figure out what is the change in the electric potential. Okay, so VF, so we need to figure out VF and VI, the final electric potential and the initial electric potential. So VF is going to be equal to KQR, and VI will also be equal to KQR. And the only thing, the K and the Q will be the same, but the R value will be different. So for the so K is going to be 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. Q is the value of the fixed charge, so it's going to be 4.4 coulombs. And for the final, we want to know how it would be 2 meters away. Okay, so the coulombs are going to cancel, or one of these coulombs is going to cancel. We'd be left with a coulomb here. One of the meters will cancel, so you're going to be left with a Newton meter over Coulomb, which is a volt. So VF is going to be equal to 2.0 times 10 to the 10. 2.0 times 10 to the 10 Newton meters over Coulomb, which is a volt. Okay, and then so that's the final. The initial, the only thing that would be different over here, so the top is going to be, the top part of the equation is going to be the same, but now instead of dividing by 2.0, we'll divide by 1.4. So then what we will get for VI is that VI is equal to 2.8 times 10 to the 10 Newton meters per Coulomb or volt. Okay, so we have our VF and VI, so we can now determine the change in the electric potential. So delta V is equal to the final electric potential minus the initial. The final was 2.0 times 10 to the 10th volts, and the initial was 2.8 times 10 to the 10th volts. So delta V will be a negative number, and it will be negative 0.8. And because we're subtracting here, our significant figures go by the place value. So since each of these went out to the 10th place, then this would also go out to the 10th place. So it would be 0.8 times 10 I'm going to check my math on this one. Okay, so 2.0 yeah, so it would be it would actually be 8.0. It would be 8.0 times 10 to the 9th volts. Okay. Okay, so now that we have delta V, now we can go ahead and figure out the potential energy and then use that potential energy to get the kinetic energy and the velocity. So delta P, the change in potential energy is equal to Q delta V. So Q is the charge, the charge of the moving particle. So it's going to be 1.5 coulombs, and then the delta V that we calculated was 8.0 times 10 to the 9th volt, which is a Newton meter over a coulomb. So the coulombs will cancel, so that the change in potential energy is equal to negative 1.0 times 10 to the 10. This should be a negative here. Okay, so this shows us that we had a decrease in potential energy. So that means then that the kinetic energy, that would be converted to kinetic energy. So the kinetic energy would be 1.0 times 10 to the 10 Newton meters or joules. Okay, then the last step then is to use that kinetic energy to determine the speed of the velocity of the particle. So kinetic energy is equal to 1/2 mv squared. So if we take kinetic energy divided by 1/2 m and take the square root of that, that will give us V. Okay, so the kinetic energy we had was 1.0 times 10 to the 10 volts, which is a Newton meter per Coulomb. And we will divide that by 1/2 and by the I'm sorry, the kinetic energy is just a Newton meter, not a Newton meter per Coulomb. Okay, we'll divide that by the mass, which we were given as 42.3 kilograms. Okay, so if we change this Newton up here to a kilogram meter per second squared, and it was a Newton meter, so there's the Newton and then meter, so the kilograms will cancel. Meters times meters is meters squared over seconds squared. When we take the square root of this whole thing, that will give us V. So, and we will be left with meters per second, and V will come out to 2.0 times 10 to the 4th meters per second. Okay, so that is number 5. Okay, number 6. We have a negative 9.2 millicoulomb charge, and it has a mass of 3.5 kilograms. And it is placed 75 centimeters away from a fixed charge that is 2.5 times 10 to the negative 3, 2.5 millicoulombs. So it's a positive 2.5 millicoulombs. And if the particle starts at rest, how fast will it be moving after it has traveled 25 centimeters? So it's going to travel 25 centimeters. Okay, so these particles are opposite, so they're going to be traveling toward each other. They're going to be attracted to each other. So that means when it has traveled 25 centimeters, it's going to be 50 centimeters from the other particle. Okay, and of course these need to be in meters, so this would be 0.75 meters, and this would be 0.50 meters. Okay, so we're gonna, the same thing is gonna be exactly the same thing that we just did. We need to get the potential energy and put the change in potential energy, because they're starting at rest, so the change in potential energy is going to be Q delta V. So the first thing we have to figure out is delta V, and then we can use that. Once we know the potential energy, we'll know the kinetic energy, and we can figure out the speed of the particle. Okay, so the change in electric potential is equal to VF minus VI. Okay, so VF is going to be KQ over R, and VI will be the same thing. Let's move this all up to the top. Okay, so VF is equal to KQ divided by R. VI is KQ Q divided by R. So K is going to be 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. Then the Q is the fixed charge, and we need to convert that to Coulomb. So it's going to be 2.5 times 10 to the negative 3 coulombs. And we will divide that by R, and we said that R would be 0.50 meters. I apologize for how this whiteboard is working today. Okay, so VF will be equal to 4.5 times 10 to the 7. It'll be a Newton meter per Coulomb. So the meters, one of these meters will cancel. That'll cancel. This Coulomb will cancel. Newton meters per Coulomb, which is a volt. Okay, so then for the initial, everything here is going to be the same for the initial, except that the radius will now be 0.75. So I'm just going to substitute that in here. This would be 0.75 meters. And so then for VI, what you're going to get is 3.0 times 10 to the 7th volts. Okay, so then we can calculate delta V as VF minus VI. So delta V equals VF minus VI. So it's going to be 4.5 times 10 to the 7th Newton meters per Coulomb minus 3.0 times 10 to the 7th Newton meters per Coulomb. So the change in the electric potential is 1.5 times 10 to the 7 Newton meters per Coulomb, which is a volt. Okay, now we can plug that in. We know that potential energy is equal to Q delta V. So Q is the charge that is free to move. So that would be the negative 9.2. I'm going to change that to coulombs times 10 to the negative 3 coulombs times this delta V that we just calculated. Which was 1.5 times 10 to the 7 volts, which is a Newton meter over Coulomb. So the coulombs are going to cancel, and therefore potential energy will be equal to negative 1.4 times 10 to the 5th joules. Okay, so that means the potential energy decreased by 1.4 times 10 to the 5th joules. So then the kinetic energy equals 1.4 times 10 to the 5th joules. Okay, and kinetic energy is equal to 1/2 mv squared. So kinetic energy divided by 1/2 m, square root of that will give us v. Okay, so then we can go ahead and plug all those numbers in. So the kinetic energy was 1.4 times 10 to the 5th. Newton meters is a Newton is a kilogram meter over second squared, and then a meter, because it was a Newton meter. And we would divide that by 1/2. And by the mass, which was 3.5 kilograms. So kilograms will cancel. You'll be left with meters squared over second squared. Take the square root of that, and you will get v, the velocity. So that leaves us then with a velocity of 2.8 times 10 squared meters per second. Or you could say that it is 280 meters per second. Okay, so that's number 6. Okay, number 7. Now we have a positive 3.8 millicoulomb charge. So I'm going to go ahead and change that to coulombs. And that the mass of that is 5 kilograms. And the stationary charge is 1.5 millicoulombs. Okay, so this is the fixed charge. This is the one that is free to move. And they're going to start out 1.2 meters away. And our question then becomes, and it's going to start with an initial velocity. So the velocity is going to be equal to 245 meters per second. Okay, so let's think through this. So they are both positively charged, so they're going to want to repel each other. But we're going to give this moving particle an initial velocity toward the fixed particle, but it will, because they want to repel each other, it will go toward that charge, but then it's going to eventually stop and move the other way. And we want to know how close will it be before it stops and moves away. Okay, so in this case, now we can figure out the kinetic energy. And then once we know the kinetic energy, we can get the potential energy. So kinetic energy is 1/2 mv squared. So that's going to be equal to 1/2 times the mass, which is 5 kilograms. And then we're going to square the velocity. So it's going to be 245 meters per second. And we'll square that. Okay, so the kinetic energy is going to be equal to 1.5 times 10 to the 5th joules. Okay? So when this particle stops and then turns back the other way, all of that kinetic energy will be potential energy. Okay, so then that means that we can then take the change in potential energy is going to be equal to Q delta V. Okay, so the initial potential energy was 0, and the final potential energy is going to be 1.5 times 10 to the 5th. Okay, so we can then solve for delta V. So delta PE divided by Q will equal delta V. Okay, so this is going to be 1.5 times 10 to the 5th Newton meters divided by the charge on the lowercase q is the charge that is free to move. Okay, so we're going to have a Newton meter over a Coulomb, which is a volt. So this will be equal to 3.9 times 10 to the 7 volts. Okay, so that is going to be delta V. Okay, so now that we know delta V, and we know how far apart these particles were when they started, we want to know how far apart they were when it stopped, the particle stops and turns around. So we can go ahead and figure out VI. We know delta V, and we know VI. We can figure out VI. So delta V so we just said that delta V is equal to 3.9 times 10 to the 7 volts. Okay, so delta V is equal to VF minus VI. So delta V plus VI will give us VF. Okay, and we need to know VF if we are going to be able to figure out the radius. So let's go ahead and figure out VI. We know we have the information that we need for VI. VI is KQ divided by R. Q is the fixed charge, so 1.5 times 10 to the negative 3 coulombs. And then the radius, they were initially 1.2 meters away. Okay, so one of these coulombs will cancel, one of these meters will cancel, that meter will cancel, so that VI is equal to 1.1 times 10 to the 7th Newton meters over coulombs, which is a joule. Okay, I'm sorry, which is a volt. Okay, so now we know delta V, we know VI, so we can get VF. So this is going to be 3.9. I have to 3.9 times 10 to the 7 volts plus 1.1 times 10 to the 7 volts is going to be equal to VF. So VF then is 5.0 times 10 to the 7 volts. Okay, then with that information then, we can determine the radius. The point at which they will turn around. So the final voltage is equal to KQ divided by R. Okay, so we're going to solve for R. So VF, or KQ divided by VF will equal R. So 9.0 times 10 to the 9th Newton meter squared over Coulomb squared times the Q, which is the fixed charge, and then we would divide that by the VF that we calculated, which was 5.0 times 10 to the 7th Newton meters over coulombs. So the these coulombs will cancel, and the newtons will cancel. One of the m's will cancel, so you'll be left with meters, and that's what you should have for R. So then what you get for R is that it will be equal to 0.27 meters. So that means that that particle is they're going to start 1.2 meters apart. This particle will move towards this particle until they are 0.27 meters apart, and then it will turn around and go back the other way because those particles are repelling each other. Okay, number 8. Okay, number 8, what is the electric potential of a 3.2 times 10 to the 6 Faraday capacitor when it stores 0.50 coulombs of charge? Okay, so for this question, we will use our equation for capacitors. So V is the electric potential, and that is 0.50 coulombs. No, that's not right. Is that right? Q is the charge that it stores. So this would be 0.50 coulombs. And the capacitor, we are told, is 3.2 times 10 to the negative 6 farad, which is a coulomb per volt. Okay, so your coulombs are going to cancel. You're going to be left with volts. And V will be equal to 1.6 times 10 to the 5th volts. Okay, so in this problem, the uppercase Q is the amount of charge that is stored in the capacitor, and this variable is the charge on the amount of the capacitor itself. Okay, so that's number 8. Number 9, we have a proton that is 1.6 times 10 to the negative 19 coulombs. So this is a proton. So that means it's positively charged. Its mass is 1.7 times 10 to the 20 times 10 to the negative 27 kilograms. It's placed at the edge of a positive plate in which the capacitor, so that would be CQ, is equal to 1.4 times 10 to the negative 6. Farad. And then we want to know how fast. Oh, okay. Also, we are told that the capacitor holds 2.2 millicoulombs of charge. So that would be 2.2 times 10 to the negative 3 coulombs. That's going to be equal to uppercase Q. Okay, so then we want to know how fast will it be moving when it reaches the negative plate of the capacitor. Okay, so it's nothing new. It's just going to be application of all the formulas that we already know. Okay, so if we can figure out the change in electric potential, then we will be able to figure out the potential energy. If we can figure out the potential energy, we can figure out we know the kinetic energy, and then from that we can get the velocity. Okay, so the first thing we need to do is figure out what is the electric potential. Okay, the electric potential is Q divided by C sub Q, okay, lowercase q. So that's going to be equal to the charge on the capacitor, or the charge on the charge of the magnitude of the fixed charge. So it's going to be 2.2 times 10 to the negative 3 coulombs, and we will divide that by the capacitor, 1.4 times 10 to the negative 6 Faraday, and a Faraday, we've already said, is a coulomb per volt. Okay, so coulombs are going to cancel, and so the electric potential that we get will be 1.6 times 10 to the third volts. Okay, now the other piece of information you need to know is that the problem tells us that it's placed at the edge of the positive plate and it moves toward the negative plate. So if it goes from positive to negative, that means that there is a decrease in electric potential, so a decrease in V. So that means that it's going to be a negative 1.6 times 10 cubed volts. Okay, so now that we know that, we can go ahead and figure out the potential energy. So potential energy is equal to Q delta V. Okay, so Q is the other charge, the charge that is moving. So that's going to be 1.6 times 10 to the negative 19 coulombs. And we will multiply that times this negative 1.6, what we calculated as V, negative 1.6 times 10 cubed volts, which is a Newton meter over a coulomb. So coulombs are canceled. You're left with Newton meter, which is a joule. So what you get for potential energy is a negative 2.6 times 10 to the negative 13. Newton meters or joules. Okay, so that's our potential energy. So that, and the negative tells us that the potential energy decreased by that much. So then we know that that all became kinetic energy. So kinetic energy is positive 2.6 times 10 to the negative 13 joules. Okay, now with that kinetic energy, we can determine the velocity. So again, kinetic energy is equal to 1/2 mv squared. So kinetic energy divided by 1/2 and divided by m, and take the square root of that to get v. So what we had for kinetic energy was 2.6 times 10 to the negative 13 joules, which is a Newton meter, and we'll go ahead and change that Newton to a kilogram meter over second squared. So there's our Newton, and then you have another meter, and we will divide that by 1/2 and divide by the mass, which the problem gave us as 1.7 times 10 to the negative 27 kilograms. Okay, so the kilograms will cancel, meter squared over second squared, but we're going to take the square root of this whole thing, so that what we will get for the velocity is going to be 5.5 times 10 to the 5th meters per second. Okay, so as that proton is moving from the positive plate to the negative plate, it will be moving at a velocity of 5.5 times 10 to the 5th meters per second when it reaches the positive plate. No, when it reaches the negative plate, it's going from the positive plate to the negative plate. Okay, last one, number 10. Okay, so number 10, we have an electron. So that electron is going to be our lowercase q, and it's going to, since it's electron, it's negative 1.6 times 10 to the negative 19 coulombs. And its mass is 9.1 times 10 to the negative 31 kilograms. And this tells us it's going to be moving from the negative plate to the positive plate. So that tells us that we are going to have an increase in the electric potential. And then the last bit of information that we have is that the capacitor is 5.1. So this would be CQ is equal to 5.1 times 10 to the negative 6 Faraday. And this says if it starts from rest and reaches a speed of 3.2 times 10 to the 5th meters per second, how much charge was stored on the capacitor? So it starts at 0 meters per second. It's going to end at 3.2 times 10 to the 5th meters per second. And it asks us how much charge was stored on the capacitor. So the charge that is stored on the capacitor is uppercase Q. Okay, so this particle is starting at rest, and it's going to end up at 3.2 times 10 to the 5th meters per second. So that means we have enough energy to figure out how much kinetic energy it will have when it has reached that velocity. So the kinetic energy is 1/2 times mv squared. Okay, so it's going to be 1/2 times the mass, which is 9.1, times 10 to the negative 31 kilograms, and then we'll square that velocity. 3.2 times 10 to the 5th meters per second, and that is going to be squared. So the kinetic energy will be equal to 4.7 times 10 to the negative 20 Newton meters, which is a joule. Okay, so if we know that is the kinetic energy, then we know that that kinetic energy came from potential energy. So therefore, the potential energy is going to, it decreased by, we started with all potential energy, and that potential energy decreased by that amount. So it would be negative 4.7 times 10 to the 7th joules. Okay, so now what can we do next? Well, since we know the potential energy, we can figure out the change in the electric potential. So delta PE, the change in potential energy, is equal to Q delta V. So change in potential energy divided by Q will give us the change in electric potential. So negative 4.7 times 10 to the negative 20 joules, which is a Newton meter. And we divide that by the charge here that we were given for Q, negative 1.6 times 10 to the negative 19 coulombs. Okay, so we have a Newton meter over Coulomb, which is a volt, so that delta V will equal 0.29 Newton meters over coulombs or volt. Okay, then the last step that we need to do then is, now that we know delta V, we can figure out the charge that was on the positive plate. So we know that the change in is equal to Q divided by CQ. So delta V times the capacitor is going to be equal to the charge on that plate, the charge that is stored on the positive plate. So we figured out that delta V was 0.29 Newton meters over coulombs, that's a volt, times the charge of the electron was negative 1.6 times 10 to the negative 19 coulombs. And that is going to be equal to Q. So if we look at the this is in a, this is yeah, so this 0.29 was in volts, and a volt is a Newton meter per coulomb. And this charge on Q is a coulomb oh, I'm sorry, I put in the wrong value here. The CQ is 5.1. I'm sorry. The CQ value that we are given, this was the charge of the particle. The CQ value is 5.1 times 10 to the negative 6. That value we were given. It's a Faraday, which is a coulomb per volt. Okay, so the coulombs are going to cancel. a Newton meter per coulomb is the same as a volt, so that will cancel. And we'll just be left with the coulomb, which is that charge. So 0.29 times 5.1 times 10 to the negative 6 will get you 1.5 times 10 to the negative 6 coulombs. That is equal to Q. So the charge on the positive plate, if the charge on the positive plate is 1.5 times 10 to the negative 6 coulombs, then that would get us that velocity that we were given initially of 3.2 times 10 to the 5th meters per second. Okay, so that is all of the problem.